this a little quicker, hopefully, because we're going to do the exact same thing. We got Pete's passengers and Aaron's passengers. What if we subtracted? So we could have 2 minus 2, right? Or 3 minus 3, or 6 minus 2, right? All the different possibilities. We could have as many as a difference of 4. We could have 2 minus 5 to negative 3. So here are the range of possibilities, and they've calculated up those probabilities. So for instance, like this negative 3, we had to have Pete have 2 and her have 6, so that is 0.15 times 0.1, which is 0.015, and they've calculated that. And difference of 0 could happen a few different ways. We could have 2 and 2, 3 and 3, 4 and 4, or 5 and 5. So this probability here would be 0.15 times 0.3, or 0.2, right? So plus 0.25 times 0.4 plus this times that, and so you can calculate each of those probabilities. They've calculated up some variances and standard deviations for us again, and what do we notice? These numbers might look familiar. This is not a typo. So the variance, do we notice a relationship between those? They still add. And that might strike you as a bit weird. We just subtracted random variables. And before, when we subtracted constants, we knew that, like, well, I guess it didn't affect our spread, but, you know, subtraction made sense. Here, we're subtracting random variables, but our variances are still adding. So by removing, like, if we do Pete's minus Aaron's, there's just as much variability in the difference as there is in the sum. And it makes sense eventually if you think about it, but it's kind of weird. It's kind of counterintuitive at first, but variances add against standard deviations don't. And so we've actually followed the exact same rule, even when we're subtracting. So when we're doing the difference of those, and sorry, this should be a minus sign. When we're doing the difference of two random variables, we still add variances, and we still do that. So when we subtract two independent random variables, their variances still add. You could think of this as, like, if I, have like a random amount of like cereal or something, and I pour it into the bowl. I take a cup. Well, there's some variability there to the amount of cereal that goes in the bowl. Then let's say I realize, oh, I did too much. Let me remove a half a cup. Well, there's still some variability in what I'm removing. So by removing the amount that I remove is variable, we're actually adding variability to the overall, like, the amount that remains. Even though we're removing, like, the average amount goes down, the amount of uncertainty and how much is in there is going to keep adding. And if I keep actually doing that, if I keep, like, moving back and forth, if I, like, put a cup in, take a cup out, put a cup in, take a cup out, and if you eventually, like, it's the variability continues to add, and it might slowly fill up over time or slowly go down, because each addition or removal adds to, like, the potential error, like the kind of the running error. All right, so finally an application of this, and then we'll be done. That's a long one. Pete charges $150 per passenger, and Aaron charges $175 per passenger for cheap tours. And so they are giving us the standard deviations of each of those. They've calculated this out. They said define D as the difference, basically in their amount of money, their earnings. Pete's trying to show off how much more he earns on average or something like that. What's the variability? Calculate, interpret the standard deviation of D. So basically we're going to add those variances. We're going to need to square Pete's number, square her number, add them up, square root to get that variability. So that is... So we get a variance of 53.5... sorry, what is it? If we add the variances, 53,594. This is why we stay away from these numbers. They're like, it's a squared amount, and it's weird. But then if we square root, we get to a standard deviation of their difference of $232.28. And that would be the difference in Pete minus Aaron in the amount collected on a randomly selected day, typically varies by about $232.28 from the mean difference of $20. So sometimes he makes on average $20 more, but there's quite a bit of variability to that difference. If we added their two, this would be the exact same standard deviation. All right, and then last thing is about shape. Let's go pretty quick. So far, we have concentrated on developing rules for means and variances of random variables. What about shape? What happens if we combine two independent normal random variables? So if they have if both distributions are normal, we're not going to do all shapes, but if both distributions are normal, if we do the sum or difference of these two, so we've got both the sum and the difference, they've kind of shown both of those, we end up with a normal distribution. Or if they're approximately normal, we'll end up with an approximately normal distribution. So it stays the same. The mean and standard deviation of the resulting normal distribution can be found using those other rules, but the shape of two normal distributions going together will be normal. So one last one here. The diameter C on the top of a randomly selected large drink cup at a fast food restaurant follows a normal distribution with a mean of 3.96 inches and a standard deviation of 0.1 inch. The diameter of a randomly selected large lid at this restaurant follows a mean of 3.98 inches. The lids are a little bit bigger than the cups, so I guess, yeah. And the standard deviation of 0.2 inch. Assume that L and C are independent random variables. Let the random variable D, the difference, equal L minus C, be the difference between the lid's diameter and the cup's diameter. So we're going to describe the distribution of the potential difference. We could end up with a slightly bigger than average cup and a slightly smaller than average lid or something like that, and that might be a problem because our lid might not fit on our cup, or maybe our lid's too big. So ultimately we need to describe the distribution of the potential difference for these two. So the shape, they're both normal and independent, so the shape will be normal. The center, we are subtracting, so we can subtract the mean, so 3.98 minus 3.96 to get an average difference of 0.02. However, the variances add, so we go 0.01 squared plus 0.02 squared and square root to get that standard deviation. So that's our shape, center, and spread of that distribution. We have a nice little normal distribution. So then what if we ask for a lid to fit on a cup? The value of the lid has to be bigger than the value of the cup, but not by more than 0.06 inch. Find the probability that a randomly selected lid will fit on a randomly selected cup. Interpret this value. So it has to be greater, so it has to be greater than 0, but not greater than, the lid can't be more than 0.06 larger, or else it's like too loose and it'll just fall off. And so if we graph that distribution, so showing a lot here, if we graph that distribution, we're talking about numbers in this range, and this is the list of differences. We calculated that difference by subtracting means, by adding variances, basically combining of two random variables with subtraction. And so they're doing the z-score calculation. You could convert both of those values, 0 and 0.6, into z-scores based on our known mean and standard deviation. Or we could just go straight to normal CDF if we wanted to go from the lower bound of, let's see here. Yeah, sorry, these are just wrong. This must have been copied from somewhere else. So if we wanted to go straight to it, we could go from 0 to 0.06 and type in that mean of 0.02 and standard deviation of 0.0224. I'll assume that this number is correct, but I don't know if that's accurate, right? They might have done the area below this one minus the area below that one. And so that is ultimately, I mean, it looks about right. It looks like about 77%, so we'll take it. There, on second thought, because they got it right here, sorry, on this page, this is right, from 0 to 0.06 with that mean of 0.02, standard deviation of 0.0224, and that'll give us that probability. And so we can interpret that as there's about a 77.7% chance that a randomly selected lid will fit on a randomly selected cup. We can calculate it using that type of math. There's a lot of different applications of this, and so we'll do some more practice with that, but that is combining random variables.